Hello and welcome back. Here we are at week number 2, and the last time we were together on Wednesday we had gotten started with chapter 4, and over the weekend you guys probably got a couple of emails from me and encouraging you to make sure you don't fall behind. And so let me just say it again, that hopefully you've done 3 lectures with the 3 homework assignments, chapters 1, 2, and 3, as well as 2 labs. And I do apologize. A bunch of you sent me an email, and I'm glad you did. I didn't really give you a spot on Canvas to start turning in your labs. I fixed that. And some of you must have noticed that because you sent me an email. But when you go to Canvas now, you should see a spot to turn in homework and your labs. And in your labs, there's 4 listed so far. By the end of the semester, there'll be a lot more. But those 4 are what we're working up to this first exam. And so today is Tuesday of the second week, and so remember yesterday was a holiday, Monday, and so we'll have class today, Tuesday, and class again on Wednesday, and then we'll hit the weekend again. And it's summer school, so I know there's a lot of material coming kind of quickly, but hopefully with the long weekend there, both this last holiday and then this coming up, you'll have the no new material Thursday, Friday, Saturday, and Sunday. Hopefully that'll give you a chance to kind of get everything digested, if you will, to finish up all the homeworks and all the labs, because all of those are due the following Monday. And so 6 days from today, you have all this stuff we've been working for or towards due. And I hope I didn't make a mistake here by giving you so much lead time, but I thought that would be best when I was setting up this class, because it's just new. It's new to you, new to me, teaching remotely and you learning remotely, and just wanted to make sure that things were kind of falling into place before we actually had a due date. So in 6 days from today, we've got a lot of stuff due, and so I'll just say it again. On that Monday at 11 o'clock, the test will unlock, and that's where you'll just look at the test and print it out and then write on it by hand and turn it back in. So I was thinking that I don't want to change the due date on anything, because I told you I would give you all the way up till midnight. It's actually 11:59 p.m. before anything was due. I guess the exception of the test. The test is kind of timed there, and so it's 11 o'clock to 12:30, so I have to turn it in by 12:30. And then after the test, you can turn in all your homework, and you can do just that in one shot. That would be chapters 1 through 6, and then you can turn in the 4 labs. But I wanted to just emphasize that the first lab, hopefully you've already done. And go ahead and go to Canvas and turn it in. I know it's not due, but let me encourage you to turn it in, because I think that would be a good practice for you to figure out how to take something you've written on hand and how to make sure you get it into a PDF, and how to find Canvas, and then how to turn something in on Canvas. And that way, if you have any difficulties with any of those steps, you'll have time to ask me or somebody else, hey, how do you do this? Because you want to make sure you're well prepared on how to take something that you have written, which would be the test, how to then scan it or take a picture and then turn it into a PDF, and then how to log into Canvas, and then how to turn it in. And so I wanted to say that here at the beginning. Let me encourage you, if nothing else, at least lab number 1. You should already be done with it, and if you're not, do that right now. I mean, just hit pause key right now and go do that lab and practice turning it in. And I would even go further. If you had a little difficulty with it the first time, just to make sure you're doing this well, turn in lab number 2. Again, that was last Wednesday. You should have already done it. But again, that practice of just taking something you've written, scanning it, or taking a picture of it and turning it into a PDF and logging into Canvas and then just turning it in is a really good practice so that you don't mess up on the day of the test, because the day of the test, obviously the test is more crucial, and I want to make sure everybody is, you know, ready for the technical side of this remote learning. And so that way you can really then just focus on learning the physics now and doing the problems. Which leads me then to this week. And so here's what we're going to do this week. I'll hold this up here again, but the syllabus, so we went over the first day, and of course it's also on the canvas, and you also have it. It says here today that we're going to go ahead and finish up chapter 4 and start chapter 5. We may even finish up chapter 5. Chapter 5 and 6 are really short ones, and they come at a perfect time, because tomorrow it says finish up 5 and then also do and finish up 6, so that on Monday, June 1st, you're ready for the exam at 11 o'clock, which covers chapters 1 through 6. The reason I was saying I'm kind of glad they're short, because I think that will give us enough time to then go ahead and do some summary, some recap, some review, some practice problems. And so after we get done with chapter 6, I'm going to make a small video, I'm not sure how long, maybe about an hour long, that will then kind of summarize chapters 1 through 6. And we'll kind of list the formulas and list the ideas, and it won't obviously be a repeat of all of these lectures. We've done a lot of material, but it at least summarize and show the kind of problems that will be on the test, and give you a little bit more heads up and a little bit more, well, I guess basically just make you feel more comfortable of what to expect when that clock hits 11 o'clock on Monday morning. And that's the idea here. All right, so with that said, I will go ahead and continue with our lecture, although even before I continue into chapter 4, let me just pause. I wrote myself down 6 different problems that I got a number of questions on over the weekend from you guys by email. And I thought it might be good for everybody to kind of recap those, especially if anybody was struggling on it. But even those of you who did it right, it might be nice to see maybe a different approach, maybe my thinking about it, and I think it will add some clarity. And so I'm going to begin today with addressing some of these for lack of a better word, more challenging one. And so I really didn't get any questions from chapter 1, and rightfully so. But I grabbed 2 from chapter 2, and then 4 from the harder chapter, chapter 3. And that kind of makes sense. The chapters have been getting harder, so I got almost really no questions directly about the assignment. I had other questions about procedurals from chapter 1, but really no questions. And I've got really these 2. So let me come over here and say, let's look then at this problem here. Chapter 2, let me come back, I think it was number 24. And let me work through that one. I'll read it first just to kind of recap here. But it says here, a rock is dropped into an abandoned mine, and a splash is heard 4 seconds later. It then goes on to say, assume that the time it takes for the sound to travel back up the mine shaft can be neglected. And so in other words, that's a small piece of it. Determine the depth of the mine shaft and how fast the rock was falling when it hits the water. And there's really 2 ways to approach this. And the reason I think I got a lot of questions on this is I noticed the solution manual, and most of the questions centered around this equation. And so I want to address that equation. It's a useful equation, but it's one I didn't give you, and it's one I don't think you see in the book anywhere directly. It is there, and I did give it to you. You got to work it out, and so that's what I want to show you. But let's do this problem. Let's do this problem 2 ways. Let me put this way, the way that your author did it on hold. Let me just kind of do it the way I kind of explained. Let me start with the speed. So if I write this, that acceleration is change in speed over the time taken, and I rearrange it to say the change in speed is then acceleration times time, and I'll just use time here instead of a delta t. But since we drop it, we know the acceleration is roughly 10. You could use 9.8 to be more accurate, but just to keep things kind of simple here in my head, I'm going to put the free fall of 10 for 4 seconds, coming up with a speed then of 40 meters per second. And again, our unit analysis, notice that the seconds cancel off. And so after 4 seconds, then we're going at 40 meters per second.
The apparatus is blocking it.
Oh, and just told that that's blocking it. Let me put it over here, 40 meters per second. That good? All right. So there's the change in speed. Now I should, again, just to make it a little more clear, this is the change in speed. And so this would be something like final speed minus initial speed. But they did say that the object is dropped, the object is released. And so they're saying, or implying in that problem, that the initial speed is 0. So the final speed is 40. It changed by 40, yes, but also the final speed is 40. And so this is the real key to the problem, though at least the way I explained it. I said the distance that something would move would be equal to its average speed. And I'm going to use the math symbol of v with a bar on it here, multiplied by the time. And so the average speed, as we saw back in chapter 2's lecture, is go ahead and take the beginning speed and add it to the final speed. Those are your two numbers, and then add them together and divide by 2, because that's how you get an average, right? The average of two numbers is you add them together and you divide by 2. And then, of course, if that happens for 4 seconds, and I should have put meters per second here for my units, shows that the average speed is 20 meters per second. And the time is 4 seconds. And that would give me then 80, and then seconds cancels off here, and I get 80 meters. And so this is kind of the way I was thinking about the problem and how I presented it to you. Again, this is not how the book worked it out. But I would answer this to say, okay, the speed when it hits is 40 meters per second, and the depth is 80 meters. Now, could you do all of that with this equation? Oh, well, yes, absolutely. But where did that equation even come from? And here's where it came from. It came by combining these equations together. It's this equation. Let me maybe circle this equation together with this equation, together with what we mean here by average speed. If you put all three of those equations together, you get this one. And what makes it then a nice equation to use for this problem is you don't have to do all three of them. It's already done for you. But I think the reason I got so many questions on it is that's what was throwing people off. They just had never ever seen that. So I thought I would start by showing it to you. And then that way we can use it. And it's actually a really nice equation to use when you have something that is involving a question about what's the distance and you got time. But here's what I really want you to see. You're going to see that this equation is only valid if you start with an initial speed of 0. That's why both myself and the author did not really emphasize this equation. It's a great equation, but it's limited. It only works when the initial speed is 0. And sadly, I have noticed in the past that when I use this equation, students just love to jump on it even when the initial speed is not 0, and then that's where they get the problem wrong. So keep in mind, great equation. Keep in mind that you could use it or not use it. But the most important thing is if you decide not to use it, then you got to work out these 3. But the most important thing here is you would only use it if the initial speed is 0. See, watch. Let's say I didn't plug in these actual numbers. This right here, this equation in the blue, so I'll work it out in blue, would look like this. It would say final speed minus initial speed equals acceleration times time. That's what this one is saying. It's saying the change in speed. Now, this equation here is really saying this, that distance is equal to, and if for average speed, you would take final speed plus initial speed divided by 2 and multiply by time. And that is this equation plus that equation and then that equation. Now, if, and here's the key, you take these two equations, and if you set the initial speed equals to 0, then this becomes final speed equals acceleration times time. And this one down here becomes distance equals, and it would be final speed over 2, because that would be 0, multiplied by time. And then if you take this one and put it into here, you would have acceleration times time over 2 multiplied by time. And if you rearrange it, you get 1/2 AT squared. And so for the many of you who said, wait, where'd that 1/2 come from? That makes no sense. This is where it came from. It came from when you are getting the average speed. And others of you said, I've never seen that equation, and this is what I'm trying to address. Well, directly true, but you have seen these individual ones. And so I'll say it again. Very nice equation. I'll even use it in the lab today. And so when we do the force and motion, why don't I go ahead and use this? That was another reason I thought it might be good to run through that equation. But I will always keep reminding you that that equation is limited to when the initial speed equals 0. All right, but as I'm sure many of you are saying, wait a minute, initial speed equal to 0 is valid for this problem. Yes, it is. So that's why I'm quite sure the individual who did the solution manual, and I don't think it's the author of the book, said, hey, I'll just use this equation. This equation is the quickest way to get to the answer. Not realizing, perhaps, that the author didn't really want that equation to be used, only because they wanted the students to kind of work it out themselves. So I'm going to take advantage of that. But now that I worked it out with you, I'm going to go ahead and use it. And so if I put a 1/2 and I put 10 meters per second squared for the dropped rock, and I put 4 seconds and I square it, 4 squared is 16, half of 16 is 8, 8 times 10 is 80, and then the second squared cancels with the second squared, and you get your 80 meters, and sure enough, we get the same answer that we got when we worked it out, what you might call the long way, or I like to call the more fundamental way. It starts from basics, and so I'll just kind of summarize this to say, hey, feel free to use this equation now that we derived it, and hopefully answered a lot of questions of where it came from. You feel free to use it. Just remember its limitation. If you have a problem where the initial speed is not 0, do not use that. You'll get the wrong number, which is why I think this is a better option, because I could just put in the initial and the final speed right here to get the average speed. It just doesn't have to be 0. It could be whatever number it started at. Which is why I thought it would be appropriate to do the next one, which is number 26. And I won't do it completely because I actually did this one in class. If you remember, after the break, we came back and I made a chart and said, hey, let's pretend we're throwing an object up at 30 meters per second, and this says make the whole chart. So I will say, if anybody's still having difficulty with number 26, go back to the latter part of the lecture from chapter 1. I remember us taking a break and then coming right back to that, so it must have been the second lecture of day 2. Well, I'm not 100% sure what lecture it is, but I do remember that we went through that one. So I'm not going to quite do the whole thing, but I think I want to do at least the first part of it, the first 1 second, because this one says make a chart. Well, I'll just read it here. It says, a ball is fired vertically upward at a speed of 30 meters per second. Construct a table showing the height of the ball and its velocity at each second just before the ball hits the ground. And I'll say it again, we made that. It was a chart, it was 6 seconds long, and you can go back and look at that. But let's just do the first 1 second with our equations. I'll start with a picture here, and so here's number 26, and so say here's the ball, and when we throw it up or fire it up, it says at 30 meters per second. 1 second later, it would have been a change of speed of 10, but remember, this was the key to this problem, that if the object is going up and the acceleration is down, that's slowing down the object. And so it changes by 10. Yes, all free-falling objects change by 10. The question is, do they change by 10 going faster or 10 going slower? And so it depends which way they're moving compared to their acceleration. And their acceleration is always down. So anything moving up is going to slow down. Anything moving down is going to speed up. And so this is that idea. And if you ask about 1 second later, so time equals 1 second, and you ask how high is it, and notice, by the way, I already did what speed is it. But the big thing I wanted to address is how high did it go. This is where it would be very appropriate to say, let's do this calculation. Let's look at the average speed. And so the object starts at 30 meters per second and then slows down to 20. So if those are your two speeds, starting at 30 and then slowing down to 20, we can average those two numbers. And so I add them together and divide by 2. And that all took 1 second. So my average speed is 25 meters per second for 1 second. And so it should have traveled a height of 25 meters. Oh, it's still, that's blocked here. Right. So this would be 25 meters per second for 1 second, which is the 25 meters. Okay, so that right there is how high it would go. And it would be a mistake to use that equation. As I was just talking about, that equation would only work if what? Yeah, initial speed is 0. And that's not what we have. And so if you were to put in 1/2 and an acceleration of 10 and a time of 1 second, I guess you're going to get 5 meters, which is way wrong. Okay? And so again, do not use this equation unless the initial speed is 0. And so that's why I say I think you're better off, if you're only going to learn one, is to learn this. Now, if you want to take that extra step and have this equation or make a little note for your test that is coming up on Monday. And so, yes, it's open book and open notes, so you can go back and look at your notes. I would say put this in your notes and say, okay, here's my formula, but over here on the side, make sure you make it very clear if and only if, this is this, IFF, if and only if the initial speed is equal to 0. Then you can use that. All right, well, I thought I would address that. Let's flip over to the next harder chapter. And so number 3, and I could tell by the questions I got, you guys are beginning to see, and this is always true whether it was face-to-face class or not, it just seems like I get a lot more questions in chapter 3 than I did in chapter 2, and almost nothing in chapter 1. And so that's exactly what I'm getting from you guys. It just got, what I'll say, real in chapter 3. And it's going to get even more real in chapters 4 and 5 and 6. Although they're kind of short, and so they're maybe not as hard as 3. Who knows? And coming up, I think of really the chapter 8, I think, is the hardest one, but no, I shouldn't even go there, because that's way down the road. That's way after test 1, and we're just trying to focus on test 1. So the first 2 come from the conceptual side of chapter 3, and I wrote down here number 19, and so let me just read it here. It says, you apply a 75 Newton force to pull a child's wagon across the floor at a constant speed. Now let me draw a picture. So chapter 3, number 19. Maybe here's a picture of a wagon, and you are pulling it with a force of 75 newtons. So notice I drew the object, and notice I drew an arrowhead. This is what we call that free body diagram. And so some of you are asking, what really is a free body diagram? Let me say it again. A free body diagram just simply is our way of trying to understand the problem and trying to draw the forces on that object. Because remember, Newton's 3 laws of motion have to come into play here. And in this case, we're talking only about a single object, so I'm only going to be using Newton's first and second law here. But they say something really, really important that it's so easy to overlook. They say you pull it at a constant speed. So what does that say the acceleration is? And so remember, the definition of acceleration is the change in velocity time taken. And so that leads us to the acceleration equaling 0. That's a key step, because that also leads us back to Newton's first law. Remember, Newton's first law says that if you have these balanced forces, an object will continue with its same speed. It's only when you have unbalanced forces does it accelerate. And so as I was saying, the first law kind of helps us and says, is it or is it not accelerating? Where the second law lets us calculate how much it is accelerating. The point I'm getting at here, that first sentence then, tells me that there must be some kind of additional force, some 75 Newton force, because this right here tells me that the net force, which is mass times acceleration, which in this case would be the mass times 0 acceleration, is 0. And so the first and the second law are really saying the same thing right here, that you got to have a net force of 0. If something moves at a constant speed, that has a 0 acceleration. That is what the first law is saying. It has a set of balanced forces. So if you're pulling it with 75, something else is pulling back with 75. And I'll keep reading, because I only read the first sentence here. But the first sentence tells me, and in fact maybe I should just give it a name here. Maybe I should say this is then friction. I don't know what else it could possibly be. I suppose there could be another person involved in this, and so as I'm pulling it with 75, they're pulling it back with 75. But I think what they just want you to say is there's probably some friction in the wheels as the wheels try to turn. Not necessarily that there's somebody pulling back with 75, but I do know there's got to be something pulling back with 75. Okay, so then the second sentence here says, if you increase the pull to 80 newtons, will the wagon speed up to some new constant speed, or will it continue to speed up indefinitely? And explain your answer. All right, so let me draw another free body diagram here, and I'll even put free body diagram. And so here's my wagon. And so what they're saying here is you've increased your pull. This was kind of what you did at first, okay? Then you increase it to 80. And here's where the problem can take two different directions. And the author's not as clear as he probably could be here. I think he's trying to imply that wherever this 75 was that was pulling back stays there. It doesn't increase, it doesn't change to anything. If it's a person pulling, they're still pulling back with 75. They haven't changed theirs. If it's friction in the wheels because of how tight the bolts are, that stays at 75. And so when you go to calculate the net force, there would be an 80 minus a 75, and that would leave you with 5 newtons. And they don't say what the mass of the wagon is. And so as we apply Newton's second law and try to calculate what the acceleration is, we're kind of stuck. We're like, oh, I can't. I don't know what it is. Right. But at least I know it has an acceleration, and that means it goes faster and faster and faster. And as long as this is true, as long as the net force is 5, that is, as long as my pull of 80 continues to be more than with this 75, then it will always accelerating. So it doesn't just go up to a new constant speed, it just keeps going faster and 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 faster. And I think that's really what the author is after here. Now I know that this could go in a slightly different direction, because if you guys are imagining what would happen if you really did this, one of two things would really happen is as it goes faster and faster and faster, you can't continue to run in front of the wagon, and so you can't continue to keep pulling it with 80, and what happens is the wagon at some point gets to some great speed that you've got to stop pulling with 80 because it's just going too fast. And you drop down to 75, and once you drop down to 75, that equals the friction, and now your net force is 0, which means you just keep going at that same speed. So I know that in the real world, if you actually did this, it would not keep going faster and faster and faster and faster faster. It would only go fast up to your running speed. It wouldn't go faster than your running speed because you would drop down. And so that's why I said this problem can go in two directions. And when the reality of the limitation of your running speed is factored in, I would say it does go up to some new maximum speed. But the big thing here is to realize, if that's the way you're thinking, you need to realize that it would reach some new maximum speed when the net force is equal to 0. And it did that because you dropped down from pulling it at 80. And I think the author here just wants you to say, in this imaginary world where you can run at any speed you want, hundreds of miles an hour, thousands of miles an hour, then you would always be able to pull it with 80. And as you always pulled it with 80, and if the friction always remained at 75, that's a question too. Does the friction always remain at 75 when you start going faster? But assuming that is true, it would always just go faster and faster. And so he's really after the first law here to get you to realize that as long as the net force is not 0, it will accelerate. And it will keep doing that. And then, which means it keeps going faster and faster and faster. Or at least keeps accelerating forever and ever and ever. All right. So that's kind of a good one that I wanted you to see. And also tying in this is number 38. It's also in the conceptual ones here. And so number 38 says this. It says, draw the free body diagram for a parachute who has reached terminal speed. Okay, so if I take this person, and they don't say if the parachute is open or not. Maybe I'll just take the person falling down and the parachute is on their back still and they haven't opened it. I think that's what they want. And of course, in a free body diagram, we would say, okay, what's pulling the parachute down? We call that the weight, mg, and so there's the force of gravity pulling it down. And then there would be this air resistance we talked about. But the key in this discussion was to realize that as you went faster and faster and faster, you would hit more air molecules, and your air resistance would go up and up and up and up, and at some point, then, you would go so fast that this number, your friction, would equal to your weight, and that way your net force, which is weight minus friction, would equal to 0, and that means your acceleration, which is net force over mass, would be 0. And that's why you have a terminal speed. Oh, that pulls in the way here? All right, so maybe I'll put this whole line over there. F equals W, net force equals W minus F equals 0, and acceleration then, which is net force divided by mass, would also equal 0. So that's, again, here what they want. To, number one, draw the picture, the free body diagram, so you should have one force down, weight, and one force up, that's the air friction. And then the other part of this should be the acceleration, and the acceleration then should be 0. All right, so those are the two conceptual ones. And then the harder ones here, if you will, was the 21 and 24. And they do have triangles by them, and if you kind of read the introduction here, the author says that he would put little triangles ones by the ones that he thought were hard. And I thought that the 21 and 24 should really go together. Most people were asking about number 24.